Great pleasure for me to speak to you. And I want to tell you a little bit about some things we've been doing on neural networks. And you'll see that there's some connection here to dynamical systems as well. Although, and so feel free to interrupt me at any point if anything's not clear or if you think that I'm saying something wrong. And so I've gotten interested in these in neural networks in this kind of the following simple question. So there's been a revolution really in neural networks. And that revolution has come because these deep learning systems basically work much better than anything that we've used before. And fundamentally, the way they work is you have some kind of input layer where your data is fed in. Then there are a number of hidden layers, and then there's an output layer that gives you an output. So in the terms of, say, classification of images of cats and dogs, you feed a digitized version of the images into the input layer. It then does some magic, and out tells you whether it's a cat or a dog. And each of these little units works basically as following. It takes the inputs from the previous layer, weights each of them, sums them plus some offsets, and then there's a nonlinearity typically, which will tell you whether the next node is then on or off, and that's done multiple times, and this gives you an output. So there's a kind of fundamental conundrum here in neural networks, which is the one I want to discuss today, is why do they generalize so well? And the reason why this is sometimes confusing to people is because we are used to the idea, in physics at least, that we shouldn't have too many parameters. That basically, if you have more parameters than data points, then you should overfit. But we know from basic theoretical grounds that neural networks are highly expressive. That is to say that they can represent almost any function of the data. And in certain limits, they're in fact universally expressive. There's a universal approximation theorem for one layer networks, and for deeper networks, it turns out you don't need to be infinitely wide. So classical learning theory tells us that these highly expressive models shouldn't learn well. What do I mean by that? In fact, just to tell you these neural networks are highly expressive, there's a paper that's came out a few years ago by Zhang et al. It's already been cited 2,046 times. I looked up today. In less than four years. It came out in December of 2016. And what Zhang et al. Basically showed was that if they took image data, so pictures of, say, cats and dogs and other things, and then randomized the labels, then what they could get is they could get the error that their network would make on that training set of randomized labels with a relatively small number of steps could go to zero. And what you then see, of course, is as you increase label corruption on these different kinds of networks, then your error starts to climb and eventually reaches a fairly high error, which is what you get more or less on random data. And the reason why this paper, it's an understanding deep learning requires thinking generalization, was very influential is because it kind of highlighted the idea that these systems have very high capacity. They have the ability to memorize data. And the question then is why, when you give them correct image labels, do they not just memorize the data? So why do they, given that they can memorize the data, why do they not memorize the data? That's the kind of question that was raised or highlighted by this paper. In fact, if you think about the fact that neural networks are highly expressive, it shouldn't be surprising that they can memorize random data. That's what highly expressive models can do. But the question is, why did they now pick one of these memorizing functions? Why did they pick functions that learn well? You might say that what this paper really showed was not so much that neural networks have high capacity, because we knew that already, but it shows you that stochastic gradient descent, which is what was used to learn this data, to train the system, is highly efficient, because in a relatively small extra number of steps, you can learn completely randomized data. So just to remind you, if you're not learning theory, what roughly is the intuition is behind this idea that large capacity models don't work well. And it goes a little bit like this. There's a kind of bias variance trade-off idea. And so bias variance trade-off is the concept that as I, for example, increase the number of data points for my particular model, then my error will eventually go to it's basically the best that my model can do given its limitations. And that's more or less the bias. The bias is how well can the model do on the data if I had infinite amount of data. And then the variance is how well do you then generalize on new data, given that you've learned on old data, on a small subset of the data. And of course, once you've kind of saturated what your model can learn, then your variance is gone to zero, which means that your model doesn't do any worse on new data than it did on data it's already learned. And very roughly speaking, the idea is that if you increase the model complexity, then your bias will keep going down because you make your model more and more complex until eventually it can learn basically anything. But your variance will also grow. And this is the key point. So as you make your model more complex, then the model can learn a very large number of functions, including functions that may memorize the data, but not have any kind of predictive power. And so the idea is that if you increase the model capacity, your bias goes down, your variance goes up. And so there's a kind of sweet spot, an optimum between having your model too simple so that you have a lot of bias, or having your model too complex so that it overfits and you have a high variance. And this is what's taught in kind of machine learning 101 as the basic way of understanding how generalization works. Another way that you might think about the same question would be something you can see right here on this next picture. So here I have a polynomial fit that to some data. So this is something that physicists and mathematicians will do all the time. A few data points, I want to fit, say, a polynomial to it. And this is what we teach our undergraduates. If you've got a fixed number of data points, then don't fit too high of a function to it. So if I fit to this data point a fifth order polynomial, you'll see that I don't do too badly, but I have some finite variance because I can't fit all that data, but I do reasonably well. That's my fifth order polynomial. If instead I pick a 20th order polynomial, well, then I can get zero bias because I can fit this data extremely well, but I get large variance. In other words, the polynomial that I might pick might have huge oscillations that we don't think are likely to be there in the real data. And so this is the kind of bias variance trade-off in a very simple way. You make your model too simple, you have too much bias. You make it too complex, you have too much variance, and you want to kind of find a model that goes in between. And of course, the other thing you see is if I use a 20-order polynomial or any other high-order polynomial in this, I have many different ways I can fit the data. So there's a redundancy in the number of different ways I can fit the data. There's lots of functions that will, and the kind of simple argument about model capacity is that if I have a very large number of functions that will fit the data, then a large number of those will be fairly complex functions, and so I'll most likely pick one of these highly complex functions unless I have some trick, some kind of regularization, something that reduces the capacity of my model. So if I have a high order polynomial, what I might do is include some kind of regularization term that penalizes high order polynomials. Now, what I also show in this plot is a fit to this data using a very simple fully connected network with 1, 2, and 5 hidden layers. So the number of parameters goes up quite quickly from 1 to 2 to 5. What you see is that neural network finds this fairly tight fit to the data. And actually for 1, 2, or 5 hidden layers, the fit is more or less the same. And so the question would be, given that the neural network is highly expressive, which means it can express, for example, any polynomial, including any polynomial I can make of this form, then why did it not pick this function, given that the neural network can also fit this function? Why did it pick this smooth function? So one way of saying this would be, why does it regularize? What is the neural network? What regularized neural network? Why does it not pick this very complicated function? There's a few other things you can learn from looking at this little example. There are just general things that we more or less know already. This function helps illustrate it. One is that the number of parameters doesn't seem to strongly affect the generalization performance of these neural networks. Once they're large enough that they're highly expressive, so that your bias is small, then it does help to add a few layers, but it doesn't have a fundamentally big effect on it. You see that here. I've got a wide range of different number of parameters, but my model gives more or less the same kind of behavior. And this tells me that really, if we want to think about these neural networks, we should take a step away from this picture of what the parameters are doing and how they interact with each other, and take a step back and think about functions. When we think about functions, what we really mean is some kind of mapping from the inputs to the outputs, which is dependent on the set of the parameters that the system has. And so I'll be talking about functions, and I've just written something down slightly more formally here because people sometimes get confused. So let's say I'm looking at binary classification, so just cats and dogs images. Then for a specific neural network, I have an input space, which is all the images that I put in the output space, which is, this is 0 for a cat and 1 for a dog, or whatever two labels I happen to have. And so I have some training sets that I train on, and then test sets that I test on. Then I'll have a function will be a 0, 1 labeling on a string of this length, the set of the number of inputs for my training set and number of inputs for my outings, my test set, and I'll have these inputs, and I'll have a certain set of outputs, and that is basically my function. So if I have 1,000 inputs and 1,000, 1,000 inputs in my test set, the training set, and 1,000 inputs in my test set, then I'll have a function that has 2,000 inputs, and the function will be whatever values it gives on that input for a specific set of parameters of my neural network. And I can ask myself how I can obtain those parameters in many different ways, by training a neural network or by randomly picking parameters. But the point is the function can be defined or represented in this way. So what I really want to distinguish before we go further is that there are really two kinds of questions in this field about generalization. One of them is, why do these neural networks generalize at all in the overparameterized regime? So why do they work so well? Or what makes them pick the right functions? And then there's a question which is important in applications, which is, given that they work so well, can we further fine-tune the hyperparameters to improve generalization? So can you make them work better by adding layers, or by training in a different way, or by rearranging the way that the network is organized? And I'm going to mainly look at this first question, because I think this is the kind of big theoretical question that's open. I think on number 2, it's a much more complicated and diverse picture. So physicists like to do simple model problems. So I'm going to give you a very simple model problem, the kind of Boolean functions. And you could think about this a bit like the Ising model of learning. It's an incredibly simple problem, and functions are easy to define. So let me give you an example, which is relevant at the moment. Let's say that you phone the doctor, and the doctor has to decide whether to send you to the hospital or not. So, if you have a fever and you have a cough and you've lost your sense of smell, and you're perhaps a little bit older and you've got a heart problem, you're obese and you have diabetes, and probably the doctor will say you need to go to the hospital. But if these things are true, but you're young, but you've also got some comorbidities, doctor might still send you to she might still send you to the hospital. But if, for example, you've got these symptoms and you're young and you're otherwise healthy, she may say, well, to protect the hospital, I'm going to tell you to stay home and stick it out. And you can keep thinking about more of these. There's many, many options that there might be available to our doctor, and she has to decide based on these inputs whether to send you to the hospital or not. So the question would be, if I gave you a number of these examples, can a machine learning algorithm be trained to know what to do in all possible situations? And well, the first thing to think here is there's 7 questions, so there's 2 to the 7 possible answers that could be given. And the question is, how many different functions are there on this space? Well, for every set of input, for all sets of inputs, there are 128 different possible. There's 128 different bits that can be 1 or 0. So there's 2 to the n possible Boolean functions. So even for this simple system of 7 questions with a possible 120 different answers, there are 2 to the 128, or 3 times 10 to the 38 possible different functions that the system could learn. So if I give my neural network these inputs, can it then predict what it should do on the other questions that it hasn't seen yet? Well, you might say, well, given that there's 10 on the order of 10 to the 38 different functions, just telling you what it does for this small set of inputs is a very small. There's very, very many functions, basically. In this case, I have given it 5 possible inputs. There's still 123 that could be anything. So there's still 2 to the 123 possible functions that will all give you 0 error on this and give you something different on the unknown data. And so this may look like an impossible problem, but yet neural networks work very well. And part of the reason I'm going to argue they work well is that if I start looking at this data, already I see certain patterns, right? I see a pattern that if you're young, you're unlikely to be sent to the hospital, that comorbidities matter. And you can probably see that there is some kind of lower order manifold in the space of all possible answers that you're effectively trying to learn. And so for the intuition, therefore, is that for neural networks to work well, they've got to somehow pick out these lower, simpler functions that are there in the data, and not simply pick one of the very large number of complex functions that can also fit the data. So to formalize this a little bit more, I'm going to talk about something which we call the parameter function map. Okay, so what is that really? If you have a space of functions that the model can express, if the model has a certain number of real value parameters, which are some set of parameters, then the parameter function map is basically mapped as a mapping from these parameters to the function that it generates. So for example, in this case, if I keep going all the way down and I give you all the outputs for every set of inputs, then I have defined a function. The function will tell you on these 128 inputs, it'll give you this particular output as a function. And that will happen if I have a certain subset of parameters on my neural network. So once you think about this in terms of parameter function map, you can start asking yourself questions like, what does this map look like? What are some of its properties? Well, one thing we know for sure is that this map has redundancy. In other words, that there are a certain volume of parameter space will give you a particular function. And so you can ask yourself, how do these volumes, for example, vary, etc. And what we've looked at is, what do these parameter functions look like, parameter map functions look like by just simply randomly sampling a neural network. So this is an example of where we look at the probability of getting a certain function. So a function will be a particular set of input-output mappings. So for example, one function is that for no matter what question answers I give you, I just always send you to the hospital. The other one is that I never send you to the hospital. Those are two possible functions. They're very simple functions, all zeros or all ones. And then there's 2 to 128 of those functions. So there's a number of interesting things. We randomly sample parameters and then look at what function you get, and then we keep track of that, and you see how frequently particular functions appear. So the first thing, which is kind of interesting, and we think is probably universal, is that this probabilities versus rank shows Zipf-like law, so 1 over R scaling. And in fact, because we know exactly how many functions there are, you can, if you know that the probability goes as 1 over R, you can normalize it, and that gives you this Zipf's law, and a zero parameter fit basically fits the way that the probability of getting certain functions. And then what we also show in this paper at the bottom there is that we can ask ourselves whether these functions that are highly likely to appear are special in one way or the other. And so what we, for example, did is we looked at the complexity of the function, and by the complexity we took a Lempel-Ziv, a particular version of Lempel-Ziv as a compressor. And what you see here is that functions that are highly likely to appear upon random sampling are also very simple. In fact, the most likely function you're going to get upon random sampling is a function that gives you all zeros or all ones. And then as you go to more complicated functions, the probability goes down. And this, I think this might be kind of intuitive. It tells you something. It tells you that if I look at the volume of the space of parameters, or maybe the probability that upon random sampling a parameter, I get a particular function, then I might intuitively assume that if the function itself is simple, then there are lots of ways of representing it in this neural network. And so I should have a large volume of the parameters, or a large probability of getting it. And as the function becomes more complicated, because it needs more information, I need to specify more of my parameters in order to describe it. That's one kind of intuitive picture. The other thing I just wanted to point out here with the probability of these functions, this is a kind of prior, it's the prior probability that you get a function upon random sampling or at initialization. I want to point out that these probabilities are very high. So the mean probability of these functions is 1 over 10 to the 38, on the order of 3 to the 10 to the minus 39. So if the functions were all equally likely to appear, I should never see a function more than once on the kind of relatively small amount of sampling that we've done here. But you see that there's a small subset of functions here which are extremely highly likely to appear. There are many orders of magnitude more likely to appear than the mean probability of all functions that this thing can express. And so I'm pointing this out to you first, and I'm going to argue a bit later why this actually matters for generalization. I'm pointing out to you that these neural networks have this incredibly strong bias towards simple functions. And the question would be, why is that? And what does that do? And why does this bias matter? Well, here's an example of why the simplicity bias aids generalization. This is a kind of Occam's razor type of argument. So what this is saying is, among the many functions that a neural network can express, it is going to preferentially express functions that have some kind of that are simple in a kind of descriptional simplicity. So here's an example of why that matters. So I have a supervised learning situation. I pick a target function. I train to zero error on. So what I do is I in this case, with the nice thing about this Boolean system is I have a lot of control over what I do. So I just pick a particular target function. So I'll say, for example, my target function is the real function that this doctor will have given for all possible combinations of inputs. And I pick that target function, and then what I do is I give half of those answers to the neural network, and then I ask how well does it predict on the other half of the answers. And what you see is as my target function becomes more and more complex, so as the answers that the doctor gives to the inputs are more and more complex, the error that I make on unseen data goes up, which is perhaps not surprising. The more complicated thing I'm trying to learn, the harder it is to learn. What's interesting is this is what the neural network does. So on simple inputs, it actually predicts pretty well. On complicated inputs, it predicts poorly. And up here, you see what a random learner does. So a random learner, we mean basically, instead of running a neural network to find a solution, I simply randomly look through the space of all Boolean functions until I find a function that gives me zero error on my training sets. And then I use that function to predict the unknown data, the test data. And what you see is that basically these randomly picked functions, although they give zero training error, give absolutely no predictive power at all. All they've done is memorize the data. And the reason why I get these upon random sampling of functions is because the number of functions that fit the data that but don't have any generalization power is orders of magnitude larger than this very small number of simple functions that give me good generalization. And here's another way of thinking about this. I'm going to show you this plot because I'll show you a few more of these later. So here what we do is we run independent SGD runs from different sets of initial conditions, and you see where and then you average over a whole bunch of different steps. So here I've got a target function which is around here at relatively low complexity, and you see that my neural network finds this kind of little cloud of solutions. It's typically solutions with low generalization error and a complexity which is on the order of the target complexity. In fact, it's slightly biased towards finding functions with lower complexity, but that's what it more or less does. My random learner, on the other hand, finds functions more or less at random with this distribution of generalization errors and this distribution of complexities. It basically always finds relatively complex solutions. And if I instead train it on a very complicated function, so a function that has high Kolmogorov complexity or high implicit complexity, then both my neural network and my random learner more or less do the same. So this is telling us that this neural network has an inbuilt kind of Occam's razor because it has a very high prior probability to get simple functions, and that this leads to good generalization on functions, on trying to learn functions that are simple. And why is this good? Well, we have an intuition that a lot of the data that we look at in practice, so data that we try to learn, is structured in some way or the other. So it's relatively simple in some kind of Kolmogorov sense. And that's basically what we're arguing here. Now, this argument is relatively straightforward. We empirically show that there is a bias towards simple functions. We show that simple functions generalize better, and this explains why the neural networks don't overfit. Although they could, in principle, fit any one of the functions that fits the data, they have a kind of inbuilt regularization, which is a bias towards simple functions, and this is a good thing for generalization. But you might say, well, okay, you've shown this to be true for these very simple systems. Can you show this is more generally true? Well, what we've also done recently is more a direct calculation for the perceptron, where you can make some nice proofs. So we've proven, for example, that if I take a perceptron, which is essentially like a zero-layer neural network, I just take all the inputs and run them through a nonlinearity and then get an output. What we've been able to show, for example, is if you take binary so if you take Boolean inputs and you ask yourself what's the output going to be, that a perceptron, at least one with a no bias function, has this very interesting property that the probability that it picks a certain number of ones and zeros is basically equal for all possible sets of ones and zeros. In other words, the probability that it finds a function with all zeros is equal to the function that finds a function with one zero or 1 1 and the rest zeros, are the same as probability that finds a function with 2 1s and all zeros. But of course, there are a lot more functions with 2 1s and the rest 0 than there are a function with just 0. And so as you get more and more complex functions, a function with more entropy in the actual in the sequence, then the individual probabilities will go way down. And this is a kind of this tells you that you will get a bias towards simple functions, and it also tells you why the simplest functions, just zeros and just ones, are the most likely, because there's only 2 of those, and the probability is equal to the probability of any other function with any other function as a set of any other functions with a fixed number of ones and a fixed number of zeros. So in this case, we've proven this, but this is still only really for the perceptron, which you can think of as kind of the last layer of your neural network. We have some proofs that we can make, which are not quite as strong, but they suggest that this bias becomes stronger as you increase the number of layers. And so I want to take a step back now and say, why do we think that why did we try to look for this kind of simplicity bias, and why do we think this is actually a generic property of these kinds of input-output maps? And there, I'm going to lean heavily on the work of one of your alumni, Kamal Dingle, who was my default student, who helped me understand this. So the intuition about input-output maps more generally, or even something like these neural networks, is what I call a monkey intuition. And this is from an old trope that goes back to Borel and possibly even earlier, which is, what's the probability that a monkey typing on a keyboard gets us a particular output? So how likely, for example, is a monkey typing onto a keyboard going to generate pi? Well, let's say if I've got 50 keys here on my keyboard, then the probability that the monkey types pi is 1 over 50 to the power m plus 1 if I have m digits. I say m plus 1 because it's got to get 3.14, right? So the first 3 digits, you get 4 things right. And so this is the probability that the monkey will type pi by randomly typing. This is actually true for any sequence of this length. That's the probability that the monkey will type it. So we'll type pi or any other any permutation on this with equal probability. What if instead of typing into a typewriter, okay, the monkey types into a computer program, say like the program C? Well, there we know a few things. So there is a competition, in fact, to make the shortest C codes for various things. And one of them is the shortest C code to generate pi. And here is a little piece of C code by Dick Winter from Amsterdam that tried to that calculates pi to the first 15,000 digits correctly using a spigot algorithm. It's only 132 characters long. So now something interesting happens. If the monkey's typing into a C program that somehow recognizes programs, then it will just need to type 133 characters correct, and 15,000 digits of pi will come out. And this tells us that numbers that are algorithmic, so numbers that have some kind of short algorithm to describe them, are highly likely to appear upon random sampling of this laptop. And the intuition behind what's happening in neural network is, neural network is not directly looking inputs to functions. It's using some kind of you're typing into the neural network, which is randomly setting the weights. And when you randomly set the weights, it's a bit like the monkey typing on a typewriter. And the question is, what functions will it find? Well, it's going to find simple functions or functions with short effective codes more likely than functions with long effective codes. That's the intuition. But this intuition has been formalized very beautifully in the field of algorithmic information theory, which I'm sure you're familiar with, but if you're not, I'll just run through some of the basics. So the founders, Kolmogorov and Chaitin, were wondering, what is the complexity of a single string? And the intuition is that if I have a string like this one, which for example is 0, 1, 50 times, then it's a simple string, whereas this one, which has no discernible pattern, is probably complex. And the way you can formalize this is to say, well, the Kolmogorov complexity, the Kolmogorov complexity of a string is the length of the shortest program that will generate that string on a universal Turing machine. And these theorems are very powerful because there are the universal Turing machine is universal, and if I pick one universal Turing machine, I can always define a Kolmogorov complexity with respect to a particular universal Turing machine. And if I want to have a different universal Turing machine, I can always use a compiler to go from one to the other. So there's an invariance theorem that tells me that this property is to asymptotically up to, say, compiler-like terms, independent of the universal Turing machine that I use. It's an actual property of the string. And it's very interesting also from kind of questions of foundations of mathematics. So you can't calculate it formally because it's linked to the halting problem, and which is against linked to Gödel's undecidability. And it also gives us an interesting intuition. So if I ask myself, for example, what is the complexity of a random, what is a random number, then you can define a random number as a number that does not have a code shorter than just print the number. That's roughly what that means. There's other intuitions, such as if I have a set, then the complexity of the set can be a lot less than the elements of the set, by which I mean, for example, if I say, give me a set of all numbers from 1 to googolplex, that's a relatively simple description, so that set is simple, but individual numbers in that set may be very complicated. And so this is an intuition that I'll use in just a minute. In fact, the idea of Kolmogorov complexity was first introduced by an American thinker called Ray Solomanoff, who was wondering about the following question. If I have a universal Turing machine and I just randomly type inputs, how likely am I to get a particular output? This is exactly the monkey intuition. So let's say for simplicity, I have a universal Turing machine that takes binary code. So the code's just a series of zeros and ones. And let's say that they are self-delimiting codes, or what's called prefix codes, which means that if I type the sequence, if it actually is a program, I'll know there's no need for an extra code word that tells me now run the program. And just for technical reasons, that's useful. So what he then worked out is, well, if I randomly type these binary codes in, how likely am I to get a particular code? Well, it's 1/2 to the power L, so 2 to the minus L, which that's the length of the code. And so how likely am I to get a particular output, like say pi? Well, it's a sum over all codes that give me pi times the probability that I get that code, which is 1/2 to the power of the length of the code. So that sum has as its first term and its largest term the simplest description of that output, which is effectively the Kolmogorov complexity. Plus there are higher order terms. So in that sense, he had come up with the idea of Kolmogorov complexity. Some of this is called algorithmic probability. And I just point out that Marvin Minsky, the late Marvin Minsky, the great kind of AI thinker, said not too long ago, not long before he died, it seems to me that the most important discovery since Gödel was the discovery by Chaitin, Solomanoff, and Kolmogorov, the concept called algorithmic probability. Everyone should learn all about that and spend the rest of their lives working on it. So I like to quote that because that's what I'm working on at the moment. And I think it's a super interesting idea here, because what Solomanoff effectively told us is that intuitively, simpler outputs are much more likely to appear than complicated outputs upon random inputs to any kind of universal Turing machine. Now, of course, in this case, he only has a first term, so this is a kind of lower bound on the probability. There may be lots of higher order of larger terms. And what's very profound, this is proven by Leonard Levin already back in the 70s, that lower bound also has an upper bound. And the upper bound is basically similar to lower bound up to some order, what is called order 1 terms. And order 1 terms are terms that don't depend on the actual X that you're trying to learn. So this is a really beautiful theorem that I think should be taught, to undergraduates in physics and mathematics, because it's a very powerful thing. It tells us that, it tells us this monkey intuition that I was throwing at you can be formalized in this incredibly beautiful way. Now, why has this not been widely taught? Well, it's because there are some formal problems with it. First of all, many things that we're interested in aren't universal Turing machines. Kolmogorov complexity is formally incomputable because of the halting problem. And then there's these pesky order 1 terms, which are things that we don't really know how to calculate or how to even bound. And so for mathematicians, this can be very, and I think understandably, problematic. So what we decided to do is to look at the same coding theory and try to find a kind of simpler and less powerful version of it that we might be able to apply in practice more easily. And so this is the work by Kamal Dingle. This is his DPhil thesis. I basically I'd observed this behavior in a lot of different systems and asked him to find an explanation for it, and eventually he came up with this. I think it's a very beautiful idea. So the first thing is we're going to think about maps. So maps are just anything that takes inputs and turns them into outputs. We're going to have maps with an input size n for which we can calculate all the inputs to outputs. So these are by definition not universe Turing machines because there's no halting problem. And the point is I can do that. That's algorithmically simple. I can say, give me this input output map, calculate all inputs, tell me what the outputs are. That's a short algorithm. That's where this complexity of the set can be much less than the elements, the complexity of the elements of the set. We can then look how frequently various outputs appear and then encode that in a very efficient way, which is the Shannon-Fallis alias code, which tells me my code length gives me a probability of getting an output, which is 1/2 to the power of its length. And this gives me a bound on the Kolmogorov complexity, given that I have a map and given that I've got a certain size of my input system. And that's a conditional Kolmogorov complexity. Given f and n, I know that's less than the length of these code words, and I can just invert this around to give me the probability that I get a certain output, give me less than or equal to 2 to the minus this Kolmogorov complexity, plus these order 1 terms, which are terms such as the ones that are the cost of the information cost of doing running through the whole set. Now, this is just an upper bound, by the way, it's not a lower bound, but this is the first step. And then what we've then did, and this is Kamal's work and then actually follow-ons to Chico's work, is that we worked out some more details of this to make this practical. So if the map is simple, so if the map of inputs outputs is simple, then so if it's order 1, or actually we think if it's order log n, then it's not too hard to show that this conditional complexity is close to the true Kolmogorov complexity. And then that doesn't help you that much necessarily because you can't calculate the Kolmogorov complexity. But then we did a typical physicist thing and said, well, let's try to calculate it anyway, and we'll use some kind of compressor or some kind of other Kolmogorov-like approximator. And then we'll simply say we'll put a prefactor in front of it in case our approximator is off by a multiplicative factor, and we'll put another factor to the side which captures the order 1 terms and the fact that perhaps our estimator is off by a constant. And what we can also prove is this bound is tight for most inputs, but not for outputs. We don't have a lower bound, but we can prove, which we just recently did, a statistical lower bound on this. So you're likely to get, this bound is likely to work well if you randomly sample inputs. And the only things we know is that the maps must be simple, they must be redundant, by which we mean in order to have a probabilities vary for the outputs, there has to be some redundancy in the map. So more inputs than outputs, basically. Map has to be non-linear because linear maps are trivial and don't show this kind of behavior. And what's a little bit less clear to us now, we're still working on, is the map can't be too chaotic in certain ways. So like, for example, a pseudo-random number generator will generate lots of very complicated looking structures, but the structures, of course, have low Kolmogorov complexity because the pseudo-random number generator is typically simple. And that's something which compressors typically can't capture. And so we can't make that work in our bounds. So the reason I'm pointing this out is that this bound is a kind of simplified version of the coding theorem by Levin, and it gives a very, very generic prediction for input-output maps. And what we then did, and this is Kamal and Chico's work, is they showed that a wide range of different maps show this behavior. So this is a mapping from the RNA sequences, which is a biomolecule sequence to structure, and you can show that simple structures are much more likely to appear upon random sampling of sequences than complicated structures are. Here is a set of differential equations, a set of coupled nonlinear differential equations that in this case describe circadian rhythm in some bacteria. And there you can have an input-output map where you randomly pick the parameters in the differential equation and ask yourself, well, how complicated is the output of the differential equation. And what you see is that simple outputs are much more likely to appear than complicated outputs. And maybe I'll give you one last example, which is L systems, which are there's a system that's originally designed for plant growth by a botanist in Utrecht called Astrid Lindemeyer, but are now used widely in computer graphics. And there again, there's an algorithmic way of designing tree-like structures or plant-like structures. And again, if you randomly pick the parameters of these algorithms, you'll see that simple trees are much more likely to appear than complicated trees, and that our bound gives a pretty good estimate of how that probability works. In this case, the blue is covered up 50% of the probability that you're going to appear. So at least half the time, or I think 90% of the time, you're going to be in this blue area. So this tells you that the bound does a pretty good job of capturing what you should really see. So that's the story about this bound. We can also break the bound, which is what you see here. There's probability complexity relationships, but it doesn't go down at all. It goes up and then back down. And this is for a matrix map, which is not simple. And so that's also good. We can break the bound when we break our conditions, which tells us that our conditions are relevant. And the reason I say this is because the input-output map for neural networks has exactly the kind of structure that you need for this coding theorem to hold. So if the coding theorem holds more generally, as we think it does for all the things that we've tested, it should also hold for neural networks, including ones where it's much harder to do a kind of simplicity bias map as we did for the Boolean system. We have been able to do probability versus complexity for more complicated systems. Here's what's called a CNN, a convolutional neural network on CFAR10, which is a more complicated image system. And we do see probability versus complexity dropping linearly, and this works. Although we have to, it's a bit more tricky to get a good measure of the complexity. We use a measure called critical sample ratio on 1,000 random inputs. So we think this holds more generally for neural networks. Now, what I've slipped under the rug, and some people are probably wondering what on earth are you doing, is that we don't train our neural networks by randomly picking parameters. So it's all good and well to say to you, well, if you randomly pick parameters, you're going to be biased towards simple functions, but we tend to train them by using stochastic gradient descent. And stochastic gradient descent is an optimizer that works on some very, very high dimensional, complex, non-convex loss landscape. So why on earth would something like a stochastic gradient descent do anything remotely like what you get upon random sampling of parameters? That's a very relevant, important question. And we've just written the paper on this that you can see on the bottom. And I want to sketch to you what the results are. And so our intuition, which I think is not an uncommon intuition for people that work on these kinds of dynamical systems, is that you should think really about the size of basins of attraction of your system. And so if I have a particular function, it could be a simple function, then I start my SGD running from some set of initial parameters, and then I will, if I'm in the basin attraction for function 1, then I'm going to go down this loss landscape until I reach function 1. Function 2 and function 3 may also give me zero error, but they're much more less likely to appear because, roughly speaking, I expect that the size of the basin, so the size of the volume of the set of parameters that give me function 1 is going to correlate with the size of my basin of attraction. And if, as we predict, the sizes of these basins, the basin sizes here, are vary over many orders of magnitude, as we saw for the Boolean system, or as we think we see for the other systems, then even though this second order, this effect will be modulated by all kinds of properties of the loss landscape, to first order, this should dominate. And the one reason we think this is because there's a whole parallel set of work that I've been doing for the last 6 or 7 years on evolutionary systems, where you also have this strong bias towards simple functions, and where you also see that certain properties that you see in nature, like for example the structure of RNAs, can be predicted based simply on the sizes of the basins. And there, of course, the real dynamics is a complicated evolutionary dynamics with complicated fitness functions. Is very analogous to the kind of search that these stochastic gradient descent is doing on these systems. And we call this effect the arrival of the frequent. The idea being that this functions with a large basin are frequent, they've got a high probability of appearing upon random sampling, and they're just going to be the ones that you're going to first find in any kind of search. So what we do here is we quantify this intuition, and I want to just show you, I'll explain to you a little bit what these graphs are. So the first thing is that we can define the probability that an optimizer gets a particular function f, given that it's trained on some training set S, and that's basically just that's an integral over all sets of inputs for the optimizer that you give, plus an integral over all sets of parameters. And as long as it finds this basin, it finds the actual basin, then that gives you, so indicator function tells you whether or not you actually find the particular function. This is what it really is formalizing, is the idea if I take a stochastic gradient sense, I give it a set of random initial conditions, how likely am I to get a particular function, given that I train to zero error on my training set. So what we did here is we took MNIST, which is an image database for numbers. We took a test set of 100 images, we binarized it so that basically 0 to 4 is 1 and 5 to 10 is 0 or something of that nature, or even though evens are 1 and odds are 0. And so we know with this binarized, even if I only have 100 images, there are 2 to the 100 possible functions, 10 to 30 possible functions that will all fit the training set, so not test set. So if I look at all functions fit the training set perfectly, there's that I can in principle find still 2 to the 100 function that will fit my test set. Of course, the vast majority of those will not generalize well, but they are all in principle possible. And what we then do is we calculate on this y-axis the probability that you are going to find this function by random sampling. The way we do this is to use a technique called Gaussian processes that allow you to work this out in a particular limit that we think is quite accurate. So on the y-axis, we have the probability that you get this upon random sampling, and on the x-axis, we have the probability that you get this in SGD. And what you see, which I think is quite surprising, is that the probability that you get a function in SGD, so this is a particular function which has an error of 1 on that test set of 100, the probability you get it in SGD, the probability that you get it in random sampling is extremely close to each other. And this is true for a whole bunch of these functions, all the functions that really matter, in fact. So SGD is finding functions with the probability more or less given to you by the probability of random sampling parameters. And to give you some sense of the scale of this, I have a different plot here where I just wrote out the probability you get a function of random sampling for any kind of error. So I pick a particular function, which is a particular sequence of ones and zeros, which is usually an inaccurate one, and then I calculate its probability. And you see that probability varies over many orders of magnitude. And so these are all functions that give you 0 training error, but some larger test error. And what you see is that the neural networks are biased towards an extremely small set of the functions, and so stochastic gradient descent. And this is super nice because if I can show that stochastic gradient descent is basically acting to first order like a kind of Bayesian optimizer, it's finding things in a kind of Bayesian way, then I can apply a bunch of nice Bayesian ideas to understand how neural networks work. Oh yeah, by the way, I can show you that not only does this picture, this function-based picture, tell you something about how well random sampling and optimization work, but you can even see things like if I use a system called pooling, which is a way of improving the way that convolution networks work on images, you'll see that the lowest error function goes up in probability both in SGD, this is Adam, a version of SGD, and in random sampling if I use pooling. So this picture also explains some things about the inductive bias, effectively, of these neural networks. And this tells you that if you use pooling, your inductive bias towards low error solutions goes up, as you expect. So the Bayesian picture is just very straightforward. I've got a prior functions, which is how likely am I to get a function upon random sampling. Then I have some kind of likelihood, which is how likely am I to get a particular training set given the function. Well, that is actually quite simple. It's 1 if I give 0 error and it's 0 otherwise. And the posterior just falls from Bayes' rule, which is how likely am I to get a certain function given that I trained to 0 error on the training set. This is Bayes' rule. And what this tells me is that, first of all, it tells me that the posterior probability is directly proportional to the prior, because it's either one, this is either 1 or 0. And also I can work out my marginal likelihood, my evidence directly. It's just a sum over all functions that give me 0 training error times the probability of getting the functions. So it's sum over all functions that fit the training set, but it's basically a constant. And then, so that's something interesting. In the last few minutes, I want to really talk about how we apply this Bayesian picture to look at how data and this bias interact with each other. So what we're going to say is, given that we've shown that SGD to first order seems to follow a kind of Bayesian sampling, so it samples the posterior with probabilities that are quite close to the Bayesian probability you would get upon random sampling of parameters, we can use that to understand in much more detail what neural networks are doing. So, and for that, we need a very nice trick that Greg Yang showed us, which is that if you take these these neural networks like the Boolean system, and you widen your initial, the width of your initialization layer. So the width of the Gaussian that you typically initialize your parameters with. Then as you increase the number of layers, and as you widen the width of your initial conditions, you start getting, you enter, there's actually a phase transition from an ordered regime to a chaotic regime. Very beautiful set of work that these people have done. And in that chaotic regime, you exactly get a condition where the simplicity bias no longer works, and simplicity bias basically disappears. To show it in another way, here's a bunch of different probability versus rank plots for different widths of those initial conditions. You're suddenly going to the chaotic regime. You wouldn't normally ever work in the chaotic regime, but it's interesting that this regime exists. And what you see is if you have a normal neural network, you get an interaction like this. And if you have a highly chaotic one, you start getting less simplicity bias. And this is super interesting because what we can show is if you start training on you try to learn functions of different complexity, then this is the normal neural network, which shows you good generalization for simple functions and bad generalization for complex functions. This more network, which has less intrinsic bias, learns less well. And here are those plots I showed you before. This is if you're learning, on a simple function, and then as you get to a more complicated function, the two networks start to resemble each other because simplicity bias no longer helps you. But for simple functions, simplicity bias has a big impact. Now, what we can then do in this Bayesian picture is a kind of pre-averaging, where we say, what's the average of the posterior if you average over a large number of different training sets? And it's not very hard to show that the probability that you this mean probability is just basically the prior, and then this the second term right here becomes just 1 minus epsilon to the power m, because that's the probability that you get a certain error given a function. And if you have a training set, sorry, of size m, then the probability of you getting 0 error is 1 minus the error to the power m. So what we did in this case is, for that Boolean system, our model system, we picked this function right here as our target function, and then we simply calculated for a whole bunch of other target functions what 1 minus epsilon is, and you get this kind of envelope here of things. So the function with the least error is obviously the one that's very simple, similar to the target function. If you make yourself too simple or too complicated, then you start seeing your errors going up, and so your 1 minus epsilon goes down. The point is, of course, if I take this to the power m, then this effect becomes hugely enhanced. And so what we then did is we made a kind of approximation where we said, let's just take the envelope of these functions, the functions that are on the top, the largest functions, the ones that are most likely to survive the mth power. And what you see is if I have a simple target function, then I get these as I increase the size of my training set from 1 to 100. You see what the training set what taking a high training set basically means is that you filter out functions with large error. And so a smaller and smaller subset of functions are able to fit your data, a training set of a certain size. But there still is a finite probability that you can fit your training data. This probability just goes down as you go away from functions that are close to your target functions. So this gives us some idea of what's happening on the data. And what we really care about is the posterior probabilities, how likely are you to get a particular function given the training sets. And so what we need to also work out is these priors. And there's a simpler way of doing it, which we'll do because we need to use this for more complicated data sets, where we, instead of working out the actual prior per function, we write the prior as a function of k, so how likely are to get a certain k. And what you have is that if you have what I should show you is, if you have functions that are in the kind of regular, the ordered regime, then this P of k is relatively flat. But if you go to the chaotic regime where you don't have simplicity bias, because there's very many more functions that are complex than simple functions, you see that your probability of getting high k goes way up, and you get this kind of scaling. And so if you multiply these P of k, which you can easily calculate by this 1 minus 10 to the power m, you can get what functions your neural network is going to find. And so it tells you that for this non-chaotic one, if this is your target function, you're going to find these functions with this kind of probability. And if you have a more complicated chaotic one, then you're going to find, although this is your target, because you're biased towards complex function, you're going to be finding these complex functions. You're going to be overfitting. And what's nice about this approximation, although it's relatively crude, is that when we apply it to problems like the one I showed you here, right, where I take different target functions, and this gives me the cloud of all the positive functions I find, here's a likelihood that I find a function of a certain complexity. What's interesting is if I use this approximation and I compare what I get from my P of k versus 1 minus m, this times 1 minus epsilon to the m, versus what I actually measure directly, it works remarkably well. Okay, so this picture is giving me basically this overall picture, which is that the reason why these neural networks generalize well is on simple input, on simple data. They have a bias towards simple functions. I can break that bias by going into the chaotic regime, and if I do that, then I see that I get poor generalization. In other words, this simplicity bias is incredibly important for what I need to see. I can do that here for MNIST. So here I have MNIST. In this case, I have 1 depth layer, 2 layers, and then 5 layers. Oh, sorry, pardon me, 5 layers and then 10 layers. And as I change the standard deviation of my inputs, I go into this chaotic regime. This here is for CFAR, which is a more complicated data set. And what I can do is the same thing. I can look at how complicated my data is for uncorrupted systems. So if I'm in the chaotic regime, which is using a network down here in the chaotic regime, or in the ordered regime, which is a network over here, I see that I get a much lower error, and also my critical sample ratio, which is a measure of the complexity, is way down. And as I increase the corruption of my data, so make my data more complex, then simplicity bias no longer really helps you in any kind of significant way, and you don't get that much better generalization error. And this is just another way of showing that the overall picture of why these neural networks generalize so well can be explained in the simple Bayesian picture. The Bayesian picture is simply predicting the generalization error in this P of k versus 1 minus epsilon k way. But I can explain to you why these neural networks generalize well. And so the story is that we think the simplicity bias is biased towards simple functions as a generic property of the world, and therefore also applies to neural networks. We show that this parameter function map stuff is incredibly important, even though SGD is doing something very complicated on the network. Effectively, it's dominated by this kind of arrival of the frequent effect. And so, although what we show in our other papers, if you vary hyperparameters on SGD, you can play a little bit with these probabilities. This is important for second order effects, so you can improve the generalization a little bit. The fundamental question, which is why do neural networks not overfit, can be understood by this simplicity bias in the prior, which carries over into the posterior. And so we think that with this little simple explanation, we have a kind of relatively complete picture of the generic question of why neural networks generalize in the overparameterized regime. And so I want to thank you for your attention, and thank the people that did the work, in particular on this neural networks. So Kamal, Ian, and Stefan were started on the evolutionary work. Kamal and Chico and Guillermo and Chris did a lot of the work on the neural networks. And I'm very lucky to have such a bright set of students. And as always, it's really the students who did all the work, and I just kind of watched from the sideline and enjoyed. And with that, I want to thank you for your attention. I'm happy to take any questions.
Yeah, thank you very much. Thank you. Any questions?
And maybe I can ask a question. It seemed to be you have some kind of general insight, or you into kind of why things work. I'm just wondering, kind of, does it help you to predict in advance whether things will work or will not work? Like, is there some kind of quantitative way of actually picking a certain problem and understanding whether you should expect a certain methodology, to work or not to work, or to be effective by means of what you have understood, or is it more qualitative?
Well, so I think it's qualitative and in this level, which is that when we're trying to think about why neural networks generalize, then the fundamental question is, given that it could pick any function to fit the data, why does it pick these particular functions? And then this is a qualitative answer for why that works. What I can show you in this picture, for example, is I can quantitatively more or less predict how well, if I make my neural network chaotic by pushing into this chaotic regime where it doesn't generalize well, I can explain to you, I can predict to you how badly it will generalize. So there I can make a pretty accurate prediction of what the generalization will be based simply on this prior and the PFK and then the data. So what this is telling us much more generally is that in order to understand the generalization neural networks, I don't think you need to understand a lot about what stochastic gradient descent is doing. I think it's helpful, but not fundamental to this big problem. I didn't talk about this at all, but we have a whole other series of a whole other kind of work plan flow where we are making quantitative predictions of a different kind. So here, what I have is you can also, there's a whole theoretical framework of bounds, and bounds are basically saying, can I predict in advance what my error is going to be on unseen data, given that I know something about my training data? And what we have is we have a bound called the PAC-Bayes, from a theorem called PAC-Bayes. What you do is you basically say, well, how like the error that I'm going to get, this is the error I'm going to get on some unseen data, is going to be, I can bound it formally by a term. This a few terms that actually are not that important. The dominant term is this term, which is log of P of U, and P of U is the marginal likelihoods of the training set. And so what it's telling me is the larger the marginal likelihood is in my training set is, the smaller the error that I am going to get on unseen data. And how well does that work? Well, here you see, as a function of label corruption on MNIST, what my generalization error is for a different kind, and this is for CFAR, this is for fashion MNIST, so different complexities of models. And what you see is that the dashed lines are what SGD does, and the straight lines are what our bound does. And so it's an upper bound, so it should always be above the data, but it gives you a semi-quantitative prediction of what the error will be, and it tells you how the error is going to change with label corruption. The other thing that we're able to predict, which I think is perhaps more exciting, is this. So in what people have shown experimentally, it's a kind of fascinating result, which is that as you look at this generalization error as a size function of your training set size. So the bigger your training set is, the lower your generalization error is. And you might ask yourself, well, how does that scale with M? So if I double M, how much lower is my generalization error going to be? This is an incredibly important practical question, because getting more data can be cheap in some cases. I'm looking at images, but it can be very expensive. I'm looking at some data which is hard to obtain. And so I might have if I'm a businessman, I might wonder, well, is it worth spending $1 million doubling my data to get better generalization? How much better will my model be? Well, what people have shown, and you see this in these dashed lines, and this is for MNIST, which is very, very simple. And this is for CFAR, which is relatively complex data sets, that basically the error scales with M to the power of minus alpha. And that alpha tends to be independent of the kind of network you use. So it would be the same for fully connected network or a CNN or something else. You might get a slightly different prefactor, but the scaling will be the same. So it's a property of the data. And it's super important because this tells me that if I have complicated system like CFAR, I get a lot less gain by doubling my data size than I do if I have a simple system like MNIST. And what we're very pleased with is that our PAC-Bayes bound, the one I just showed you, when we run it, it predicts these pretty well how these trend lines go. So I'm very, very pleased that we can predict pretty accurately what these exponents are, because that's of great empirical importance. What we're at the moment unable to do is understand where they come from, so we can predict them. That's not the same as understanding them. Right? So I can tell you that they come fundamentally from the marginal likelihood on this data, but why CFAR, I'd like to have a microscopic theory that tells me why the scaling law has the property that it has. But at least we're able to show you that it's not a property of SGD. It's basically a property of the data and the parameter function map. So that's an example of something that we can predict if you're asking for a detailed prediction.
Yeah, okay. There's a lot to take in. I think what's sometimes difficult, and despite, of course, of all your success, and also for a lot of other people in this field, is that there's a certain kind of given a set of assumptions, a given set of things, then some conclusions can be drawn, and it's very difficult to a priori understand when these conditions are really met. And this is, of course, as you say, you want to kind of derive this somehow from microscopic information in some sense, or some fundamental insight. Yeah, my basic question was like, if you are employing a certain machine learning methodology to a certain problem, how to discern whether or not certain methodology is likely to work or not, depending on what you already know about it.
Well, so what we say is our bounds here, our marginal likelihood bound, is a pretty good way of predicting it. I think the point that you're saying, which I think is so I'm giving you two kinds of arguments. One is I'm giving you a quantitative argument. I didn't give it in the talk, I just gave it to you for what you can do. This is a bound, it'll predict for you quantitatively what happens. I've given you a kind of qualitative argument based on simplicity bias and certain properties of the data for why these things work. Right? And what would be really, really great would be to do some kind of more microscopic direct, can I predict the error directly, not based on.
Well, the question, for instance, in we do dynamics mostly, so you could kind of look at different types of dynamics and see kind of like where you have good control over how regular or irregular things are, and try to kind of understand exactly. Of course, there's more toy models rather than big data sets, and you could maybe have a chance there to kind of understand a little bit because there's good control basically of the model. Hopefully, you can concoct certain type of behaviors which are increasingly more complex of a certain type, and you can maybe control that. I do appreciate that many of these data sets and stuff like that, of course, you don't really have a good control other than some empirical measure of how complex it is.
Well, with the Boolean one, you have control. That's the nice thing.
Sure.
One of my little sub stories, I think we should look for some kind of simple model that we all agree on, like the Ising model that we all study in some depth. It's interesting in this field, when I speak to practitioners, they often say, well, we're not interested in this Boolean model because it's too simple. We're only interested in real data. But I think for understanding, you need to pick something that's simpler and understand it properly first. Now, what I haven't said here as well is that we've also shown that this Bayesian prediction, which is basically ignores the dynamics entirely, turns out to do a pretty good job of predicting what SGD does, but also you can take a completely different kind of dynamics, like some kind of genetic algorithm. They're much less efficient, but they end up giving you posterior function probabilities that are extremely similar to what SGD does. And this suggests that there's nothing to first order SGD is doing something similar to what a completely different dynamics is doing. It's basically finding functions with large basins of attraction and therefore large volumes of parameters give you that particular function. And that to first order is what the dynamics is doing. The second order, all kinds, all bets are off, very complicated things are happening.
Any other questions? Yeah, I had a question actually related to last Yaron's question about the dynamics. I mean, so would this kind of results also work for when you change the architecture? So for example, you would be working with, reservoir computer, which has like memory effect in the architecture itself. So we could,
yeah, so we've done this for so we've done this plot you see here. We've done for 20 different architectures, so including resnets and dense nets and all kinds of things that have more complicated dynamics. And this prediction works extremely well for all of them. The prediction is independent of dynamics, so there's no dynamics in the prediction. The prediction is just telling you something about the parameter function map. So the fact that it works for all these different networks tells you that the dynamics is having a second order effects at best on these systems. And so it fundamentally was so people often talk about why they made a particular network architecture in these dynamical terms. We want to have memory or other things in it. I'm not saying that's the wrong way of thinking about it, but we're able to predict, for example, these exponents and how these things generalize, ignoring the dynamical story.
So it's independent of the architecture and independent of the algorithm of training.
Yeah, yeah. So I have a plot of it. No, I thought I had a plot of it somewhere, but I don't. Yeah, so it's the first, yeah, I mean, so what you need to have, in order for it to work, you need to have a algorithm that can reach zero training error. Right? So what stochastic gradient descent, I think the really interesting story about stochastic gradient descent is not really how well it generalizes, so which functions it finds, but the fact that it finds them so quickly. It's incredible. So it's an optimization problem. And as an optimizer, it works extremely well. And, you know, for those of us, I've worked on lots of optimization problems before, and it's a pretty crude optimizer compared to other optimizers that we use in molecular systems, for example. You know, there's a large history of us doing this with much more sophisticated search techniques. And so why does this particular search technique work so well on neural networks is a very deep and important question. That's an optimization question. It's a question of how come it finds zero training error so easily. So, you know, randomly picking parameters is probably the stupidest way of optimizing. And for reasons I don't. And so when we tried, you know, all these genetic algorithms, they're terribly slow. I mean, they're unbelievably slow. But when we can get them to converge, they give the same results as SGD. It's just that it's really hard to get them to converge. So it's I think that for people that are, you know, if you're interested in the dynamics of SGD or of neural networks, where I think dynamics can have an incredibly important contribution is to understand what makes them so good what makes it so good as an optimization system. What is it about the structure of the landscape that allows this, what I consider to be fairly crude optimization technique, to empirically work unbelievably well? I don't know. I have no idea what the answer to is. Something about the combination of the dynamics and the structure of the landscape. But what it is, I think, is to me a mystery.
Yeah, thank you. Any other questions? All right, thank you. Since there is no question, so let's thank you again for accepting the invitation of a nice talk. Yeah.
Well, thank you very much for
You.
I think.
Right. Thank you very much.
Yeah, thank you. I would wish the best for your father. Yeah.
Thank you very much. Yeah.
Yeah, have a good day.
All right. We'll be in touch. Yeah.